Hello. Thanks for joining us today. We are looking for someone who can really bridge the gap between the creative side and the technical pipeline in our animation and VFX department. I see you have about 4 years of experience now, which is a great sweet spot. To get us started, why don't you give me a brief overview of your recent work and where you feel your strengths lie?
Thanks for having me. It's great to be here. Over the last 4 years, I've really focused on the intersection of character rigging, technical animation, and pipeline optimization. I started out more on the generalist side, but I quickly found that I enjoy the problem-solving aspect of the pipeline, basically figuring out how to make complex artistic visions technically feasible without killing the render farm. In my last role, I spent a lot of time mentoring junior artists, helping them understand not just how to use the tools, but why the tools behave the way they do. I've handled everything from high-fidelity character rigs to setting up procedural environment tools, and I've developed a bit of a passion for optimization, whether that's reducing vertex counts or streamlining node networks in Nuke and Houdini.
That's a great foundation. Since you mentioned rigging, let's dive into that. For those who aren't as deep in the weeds, could you explain what you see as the primary function of a rigging system in a professional pipeline?
At its simplest level, the primary function of a rigging system is to create a digital skeleton for a Teen-D model, which allows animators to control its movements efficiently. Without a rig, you're basically just moving thousands of vertices by hand, which is completely impractical. The rig acts as a framework of bones, joints, and controls that define how the model can bend, twist, or deform realistically. It's essentially the bridge between the static model and the final performance. For me, a good rig isn't just about the movement, it's about the usability. If an animator has to fight the rig to get a pose, the rig has failed, regardless of how technically correct the deformation is.
Speaking of usability and deformation, let's talk about the more difficult stuff. When you're dealing with extreme character deformations, specifically things like very expressive facial animation, how do you avoid that artificial stiffness that can make a character look like plastic doll?
That stiffness usually comes from a reliance on simple linear interpolation between joints. To avoid that, I use a multi-layered approach. First, I rely heavily on blend shapes for those smooth, organic transitions between expressions. But blend shapes alone can be limiting, so implement corrective blend shapes, what some call pose space deformation, to fix distortions that happen in extreme poses. I also incorporate nonlinear deformations using tools like wire deformers or lattice modifiers to give the skin a more natural, fleshy feel. Beyond that, the joint hierarchy has to be meticulously structured with proper skin weighting, so the deformations follow the actual flow of muscles and tissue. If the budget allows, I love adding in soft tissue simulation or secondary motion systems. Just a little bit of subtle jiggle or stretch in the cheeks or jaw prevents that robotic look and makes the character feel like they have actual mass and volume.
You mentioned skin weighting there. For a complex character, that can be a nightmare and a huge time sink. What is your actual process for tackling skin weighting so it's both high quality and efficient?
I've learned that if you try to paint every vertex from scratch, you'll never finish. I approach it in manageable steps. I usually start with a base weight transfer from a simpler proxy model if one exists, or I'll use automatic skinning tools just to get a rough initial setup in place. Once I have a baseline, I move into manual refinement. I focus my energy on the high deformation areas first, the elbows, knees, and shoulders, where you're most likely to see artifacts like collapsing geometry or pinching. I use a combination of weight painting tools and a series of extreme test poses. I'll push the joint to its absolute limit to see where the mesh breaks, then I'll paint back the influence. The goal is to achieve a natural movement while keeping the weight distribution clean. Also, make sure to keep the number of influences per vertex low, because as we'll see in optimization, too many influences can actually slow down the playback for the animator.
That leads perfectly into my next question. When you're optimizing a rigging system, where are you looking for the bottlenecks? What are the red flags that tell you a rig is going to tank the performance?
There are a few big ones. First, I look at the joint count. Sometimes artists add joints for detail that don't actually influence the mesh, but the engine is still calculating them every frame. That's a huge waste. Then I look at the deformers. Overly complex, blend shapes or corrective shapes that are too dense can be a major drag, especially if they are applied unnecessarily across the whole model. Another red flag is inefficient skinning weights. If you have vertices with too many influences or weights that aren't properly normalized, you'll see a dip in performance. Finally, I check the hierarchy. A deep, convoluted rig hierarchy with way too many constraints or complex driven keys creates massive overhead during animation playback. I try to flatten the logic as much as possible and remove any unused components to ensure the calculations are as lightweight as they can be without sacrificing the animator's control.
Let's shift gears to the animation side. Imagine a scene where a character needs to convey sarcasm. This is a very subtle human emotion. How would you handle this? I'm interested in both the animation principles you'd use and the technical controls required.
Sarcasm is all about the disconnect between the words and the physical reaction. To pull that off, you need a combination of subtle timing, exaggerated but controlled poses, and asymmetrical movements. I'd start with anticipation, maybe a slight pause or a very slow build-up before the expression actually hits. Think of a raised eyebrow or a smirk that forms just a beat too late. I'd use squash and stretch, but very sparingly. You want to emphasize the cheek or lip movement, but if you go too far, it looks like a cartoon. The key here is actually the follow-through. A genuine smile fades naturally. A sarcastic one should linger just a bit too long and then dissolve unevenly. Maybe one side of the mouth drops faster than the other. I'd also add secondary motion, like a slow, lazy head tilt or a subtle eye roll. Technically, this requires very specific facial controls. You need asymmetric brow lifts and a lopsided smile controller. The timing is the most important technical aspect. The reaction needs to feel just slightly off to signal to the audience that the character is being insincere.
That's a great breakdown of the performance. Now let's move into the technical art and rendering side of things. PBR has become the standard, but there are different workflows. Could you compare and contrast the metallic roughness workflow versus specular glossiness? Which one do you generally prefer and why?
Definitely. PBR is all about simulating how light interacts with surfaces in a physically accurate way. In the metallic/roughness workflow, we separate materials into metals and non-metals. We use a metallic map to define the metalness and a roughness map to control how blurred or sharp the reflections are. This is very intuitive because it matches how we perceive the world. Something is either a metal or it isn't. The specular/glossiness workflow is a bit different. It uses a specular map to define the reflectivity and a glossiness map for the sharpness. This workflow is technically more flexible because it can represent a wider range of materials, including some complex non-metals that a simple metallic map might struggle with. However, it's less intuitive and can lead to non-physical results if the artist isn't careful. In modern engines like Unreal or Unity, metallic/roughness is almost always preferred. It's easier for artists to use, more consistent across different lighting environments, and generally produces more physically accurate results with fewer manual tweaks. It just simplifies the pipeline significantly.
Let's talk about a nightmare scenario. You're looking at a final render and you see lighting discrepancies. It looks like there's an inconsistency in how the coordinate systems or the scale are being handled across multiple assets. How do you troubleshoot that?
Those are the kind of bugs that can eat a whole day if you don't have a systematic approach. First, I go straight to the coordinate systems of every asset involved. I check for handedness. Are some assets left-handed while others are right-handed? I also verify the apaxis. If one asset is Y-up and another is Z-up and there was a bad conversion, your lighting normals are going to be all wrong. Next, I inspect the scale. If one asset is scaled at Shunya 1, and another is at 100, but the transforms were frozen incorrectly, you can get weird light leaks or shadow artifacts. I use diagnostic tools like wireframe overlays or normals visualization to see if any faces are flipped or if there's a misalignment. After that, I review the lighting setup itself to ensure the lights and shadows are being calculated in the same coordinate space as the assets. If I'm still stuck, I isolate. I'll render the assets individually or in small groups. By stripping the scene down, I can pinpoint exactly which asset is introducing the discrepancy, which makes it much easier to fix than trying to guess while looking at a full composite.
When you're matching CG to a real-world plate, what is the most critical part of that render setup?
The absolute most critical component is the lighting rig. You have to replicate the exact type, intensity, color, and direction of the lights in the original plate. Whether it's harsh sunlight, a soft interior glow, or practical lights from a lamp in the shot, the CG elements have to cast shadows and highlights that match the plate perfectly, or the eye will immediately spot the fake. Along with the rig, image-based lighting, or IBL, is huge. Using an H-dry captured on set allows the CG objects to reflect the actual environment, which provides that essential ambient light and grounding. Without accurate IBL, the object looks like it's floating on top of the footage rather than existing within the space.
Moving into compositing and technical art, let's say you're working in Nuke or Houdini. You have a complex node network with multiple input streams, tracking, rotoscoping, keying the works. How do you structure that to ensure there's minimal processing error and it doesn't become a spaghetti mess?
Organization is everything there. Start by dividing the network into modular sections. I'll have one clear area for tracking, one for roto, and one for keying. I use groups or backdrops to isolate these tasks so they don't interfere with each other. I use merge or switch nodes to logically combine the streams. To prevent errors, I implement what I call check nodes, basically using grade or expression nodes at critical points to validate the data before it moves to the next stage. If the data is breaking, I want to see it at the source, not at the final merge. I also use caching or pre-compositing for any heavy computations. There's no reason to recalculate a complex track every time I move a node. Finally, I maintain a strict naming convention and route everything through a central hub or manager node. This way, if a supervisor wants a change, I can make it in one place and it ripples through the network correctly.
In that compositing context, when would you choose to use chromatic aberration versus edge blending?
They serve two completely different purposes. Chromatic aberration is about simulating the imperfections of a real camera lens. It's that subtle color fringing you see on high contrast edges. I use it to add a layer of photographic truth to CGI because perfectly sharp CG edges look fake. It's an imperfection that adds realism. Edge blending on the other hand, is a corrective tool. Use it to seamlessly merge two or more images or layers, especially when I'm dealing with projected imagery or overlapping plates. The goal there is to soften the seams and eliminate visible lines to maintain visual continuity. So, chromatic aberration is about adding a real flaw, while edge blending is about removing a digital flaw.
Let's talk about simulation. You've likely worked with both mesh-based deformation and voxel-based simulation. When would you technically prefer one over the other?
It really comes down to whether you care more about the surface or the volume. Mesh-based deformation is all about the vertices and edges of a polygonal mesh. It's incredibly efficient and precise for things like character animation or a piece of clothing where you need a specific shape and a high level of control over the surface. However, it's terrible for things like fluids or objects that need to shatter because the mesh can't easily change its topology. Voxel-based simulation divides space into a 18D grid of small cubes. This is the gold standard for volumetric accuracy. If I'm simulating smoke, fire, or complex liquid dynamics, I need voxels because the internal behavior and the way the volume interacts with itself are the most important factors. So if I need a character's shirt to flutter in the wind, I'm going mesh-based. If I need that character to be engulfed in a realistic explosion or a splash of water, I'm going voxel-based.
Speaking of simulations, they can be temperamental. If you have a result that exhibits jiggle or numerical instability, what are the three most common root causes you look for and how do you fix them?
Jiggle is usually a sign that the solver is struggling to find an equilibrium. The first and most common cause is a time step that's too large. If the solver is jumping too far between frames, it can overshoot the target position and then snap back, creating that vibration. The fix is simply to reduce the time step or increase the sub-steps so the simulation captures finer details. Second, I look for stiff forces or constraints. If you have a constraint that's too rigid, the solver can't find a way to satisfy the physics and it starts introducing high-frequency noise. I'll fix this by adding damping or switching to an implicit integration method, which is generally more stable for stiff systems. Third, I check the geometry and collisions. If you have poorly conditioned meshes, like overlapping faces or extremely sharp angles, the objects can get stuck and then pop out violently. I'll smooth the collision meshes, increase the collision margin, or use softer constraints to prevent those erratic movements.
Let's get into some deeper technical theory. If we're comparing GPU compute shaders versus CPU compute shaders in a complex VFX environment, what are the limitations of each?
It's really a trade-off between throughput and flexibility. GPUs are monsters at parallel processing. If I need to simulate 10 million particles or render a massive fluid sim where the same operation is happening across a huge dataset, the GPU is the only way to go. But the GPU has a weakness. It struggles with complex branching, sequential logic, or dynamic memory allocation. Their architecture isn't designed for if this, then that logic on a granular level. Also, GPU memory bandwidth can become a bottleneck when you're dealing with datasets that are larger than the RAM. You're also limited by the fixed pipeline. You can't really do deep recursion or advanced synchronization easily. The CPU, conversely, is much better at irregular workloads. If I'm doing complex collision detection, procedural generation with lots of branching logic, or task scheduling, the CPU is far superior. It has much better memory management and flexibility. In a professional environment, I don't try to make one do the other's job. Offload the massive parallel math to the GPU and keep the high-level logic and complex decision-making on the CPU.
How do you handle the integration of real-time rendering, like Unreal Engine, with high-fidelity offline animation assets? That bridge can be very leaky.
It is definitely leaky. The key to managing that pipeline is a structured workflow of asset preparation, data transfer, and optimization. I start by ensuring that the offline assets, the high-poly models, and complex animation are exported in a compatible format like FBX or Alembic. But you can't just dump a cinema-quality asset into a real-time engine and expect it to run. Implement a series of intermediate scripts or tools to convert that high-fidelity data into optimized versions. This means baking complex animation into vertex animation textures or simplifying high-poly meshes into LODs while trying to preserve the visual silhouette. Finally, version control is non-negotiable. I use a system to track changes across both environments. If an animator changes a keyframe in Maya, there needs to be a clear path for that change to update in Unreal without breaking the scene. It's all about creating a loop where artists can iterate in real time, but the quality remains anchored to the high-fidelity offline source.
Let's go back to the modeling and geometry side for a moment. Could you explain vertex count optimization and why it's so critical during the modeling phase?
Vertex count optimization is essentially the art of removing as much geometry as possible without the viewer noticing. You're reducing the number of points that define the shape of the model. It's critical because every single vertex adds to the computational load. Every time the engine renders a frame, it has to calculate the position, shading, and deformation of those vertices. If you have a model with 1,000,000 vertices when it only needs 10,000, you're slowing down the render, making the animations laggy and increasing file sizes. This is especially punishing in VR or real-time games where you have a strict frame budget. My goal during modeling is to find that sweet spot where the silhouette is smooth and the detail is there for the camera, but we aren't wasting resources on geometry that's hidden or too small to be seen.
In terms of pre-production, how do you view the importance of the shot breakdown? How does that actually influence your technical planning?
The shot breakdown is basically the roadmap for the entire project. If you skip it or rush it, you're essentially flying blind. During the breakdown, the team analyzes every single shot to determine exactly what is needed, which characters, which environments, what specific VFX, and how they need to interact. From a technical planning perspective, this is where I identify the danger zones. If the breakdown shows a shot with a character breaking 1,000 pieces of glass, I know right then that I need a specific fracture solver and a rigid body dynamic setup. I can start planning the resource allocation. Do I need more render nodes for this? Do I need to build a specific tool for the artists? Without a detailed breakdown, you end up with emergency technical solves in the middle of production, which is where mistakes happen and budgets blow up. It ensures consistency across the sequence so that the VFX in shot 1 feel the same as the VFX in shot 20.
Let's test a specific scenario. You're tasked with a shot that requires simulating hundreds of interactions, like a large glass window shattering on impact. Which procedural tools or solvers would you employ and why?
For a scenario like that, I'd use a combination of rigid body dynamics and specialized fracture solvers. Specifically, I'd look toward tools like Houdini's Voronoi fracture. Voronoi is great because it allows you to break an object into fragments based on a set of points, which creates those natural-looking, jagged shards of glass rather than perfect cubes. I then use a solver like the bullet solver to handle the actual physical interactions, the collisions, the gravity, and the way the shards bounce off each other. Because these solvers are procedural, I can tweak the impact point or the force of the break without having to manually animate every single piece of glass. To really sell the shot, I'd layer in particle system for the smaller dust and tiny shards, and maybe a fluid solver if there's liquid involved. Using a procedural approach makes the simulation scalable. Can go from breaking one window to breaking 10 windows across a whole building without a linear increase in workload.
I want to pivot to something more architectural. If you were creating a procedural environment generator, what graph theory or algorithmic approach would you use to make sure the results feel organic and varied, rather than just looking like a bunch of repetitive noise?
That's a common problem. Pure Perlin or simplex noise often feels too cloudy or repetitive. To get a truly organic feel, I'd start with a Voronoi diagram to partition the space. Instead of a grid, Voronoi creates cells that look more like natural biological or geological structures. This gives me a base of distinct regions. Then I'd implement a graph-based method like a minimum spanning tree or a random walk. This is perfect for generating things like river networks or pathways that connect the Voronoi regions in a nonlinear, natural-looking way. To add the final layer of variety, I'd use noise, but I'd modulate the noise parameters based on which Voronoi region the generator is currently in. So the mountain region gets a different noise frequency than the valley region. I'd also use a Markov chain or a grammar-based system for object placement, like trees and rocks. Instead of just random scattering, the grammar ensures that a tree only appears if there's soil and not deep water, following natural ecological patterns. This layered approach moves it from noise to ecosystem.
To wrap things up, let's talk about the physics of light and cameras. Can you explain the mathematical relationship between focal length, aperture, and the resulting depth of field effect?
It's all about how light converges on the sensor. Focal length is the magnification of the lens. A longer focal length, like 100 mm, narrows the field of view and compresses the scene. Mathematically, as the focal length increases, the depth of field becomes shallower. Then you have the aperture, which is the size of the lens opening measured in f-stops. A wide aperture, which is a small f number like f/2 r, lets in more light but creates a much shallower depth of field, meaning the background blurs more. A narrow aperture, like f/solar, increases the depth of field, keeping more of the scene in focus. The relationship is inverse. As focal length increases or the aperture widens, the depth of field decreases. As a technical artist, understanding this is crucial for matching CG cameras to real-world plates. If the plate was shot at a 50 mm lens at f/2 r and my CG camera is at 35 mm, the blur will never match and the composite will look wrong.
Last question for you. If you're working on a flowing cloth object, what is the process for making that physics simulation actually feel believable?
Believable cloth is all about the balance of constraints and forces. First, the cloth is modeled as a grid of interconnected particles or vertices. Each of these is influenced by external forces like gravity, wind, and collision. The core of the simulation is the set of constraints that prevent the cloth from behaving like rubber. I apply distance constraints to maintain the structural integrity of the fabric, which prevents unrealistic stretching. Then comes the fine-tuning of material properties. I adjust the stiffness, damping, and friction. Silk requires very low stiffness and high fluidity, whereas denim needs much higher stiffness and more internal friction. Iterate by testing the cloth against different wind speeds and collision objects. Finally, I might add a bit of a windy noise field to create those subtle, unpredictable ripples that make the cloth feel alive rather than like a pre-calculated animation.
This has been a fantastic deep dive. You've clearly got a strong handle on both the high-level architecture and the granular technical details. I really appreciate the thoroughness of your answers. We'll be in touch very soon regarding the next steps.
Thank you so much for the opportunity. I really enjoyed the conversation. I look forward to hearing from you.